impedance of an inductor, you should get Li omega. If you had an extra I0, it's because I forgot to write the I0 in there. The I0 should cancel out. We're going to use this. You're going to like how we use them. To have this, I understand it would make a whole lot more sense if I went back and redid what we did before break, so that you can see that all the terms would be like this. And because it was a while ago, we're not doing it right now, you're kind of having to take my word that all the currents in the circuit will have this form, and all the voltages would have that form.
And that's independent of whether it's sine or cosine. They
Correct.
follow that form.
Correct. So for a circuit where you have a sinusoidal input, then the impedance of a resistor is R. The impedance of a capacitor is 1 over I omega C. And the impedance of an inductor is Li omega. What we're going to do is now treat, for a circuit that has a sinusoidal input, we're going to treat a capacitor and an inductor and a resistor all as if they were resistors. However, the resistance of the capacitor will not be the capacitance. It will be 1 over I omega C. The resistance of the inductor will be Li omega. So I'm going to be able to move forward with a circuit that has a sinusoidal input, that has capacitors and inductors, that would normally lead to a very challenging differential equation to solve, especially if I had 5 or 6 capacitors and 12 inductors. And I've got this little shortcut. And where we get this shortcut from is assuming that the current and voltage take on this particular form. And this particular form came from converting from a cosine to an e to the I5t in the first place. So going from the idea of going from here to here, which we did before break, that alone was a little bit of a jump. I had to use superposition. I got myself tied in knots a little bit trying to explain all that. So it was a significant conceptual jump to go from here to here. It wasn't that big a deal to go from here to here. And now I'm making another jump. I'm saying if I know the currents and voltages take on this form, I can look at this ratio of voltage to current and come up with a value of something I'm calling impedance. And I've got an impedance value for inductors, capacitors, and resistors. And I can use this information to solve circuits. In fact, I'm going to come back and do this example right here.